This is Dr.Aravind Rajan Ayagara, an associate professor at the Department of Aeronautical Engineering. In the last video, we have actually seen what are the different subsystems of vehicle systems, such as we have gone through the hydraulic systems, we have gone through the fuel systems, we have gone through the other flight control systems, and so on. And in this video, we are actually seeing the third subsystem, a major subsystem of an aircraft system, and it is one of the first non-physical subsystem. So this is nothing but the navigation system or the avionics systems. In the avionics systems, we have the navigation control systems. So what is navigation? What is navigation? Navigation is a means to direct the aircraft to its destination. So here in this figure, we are actually seeing what are the major parameters of navigation system. So here you have the barometric altitude. Altitude first. I'll just number it. Is better to number them first. Second parameter is speed. Third parameter is heading, and fourth parameter is heading relative to Earth coordinates. Fifth parameter is positions. And sixth parameter is flight legs. Flight legs is not a parameter, it is just a thing which helps to guide all the other five. So the flight altitude. Let's say that my flight level is around 30,000 feet or 11,000 kilometers. So that altitude is actually measured using barometric altitude. And you have the barometric magnetic, which is the first initial position of the aircraft. And you can see that, for example, here for measuring the heading, let us say that this red point is actually my aircraft. So this red point is actually my aircraft. So when the direction the aircraft is pointing is known as the heading, which is nothing but the true north of an aircraft. And you have the magnetic north. And we know that the magnetic north is the north pole of the earth. So when you see the heading, whenever you are measuring the heading of an aircraft, let us say that the aircraft is pointed exactly towards the magnetic north, or the magnetic north is at actually 360 degrees. The heading of an aircraft is measured in clockwise direction. So for example, if this is the true north or the magnetic north, this is at 360 degrees, you have at 90 degrees, you have east. And at 180 degrees, you have south. 180 degrees, you have the south of the aircraft. So this is how the heading of an aircraft is measured. And you also have the local position of an aircraft, where you see this is the position of an aircraft, and you have Vx, which is the velocity relative to the x coordinate of the latitude and longitude, and you have the Vy, which is the velocity of the y coordinate, and Vz is generally Vz is 0 until or unless you are doing a full lap maneuver. And the velocity or the speed of an aircraft is measured in terms of indicated airspeed or Mach number. Indicated airspeed is the one which is indicated on the flight system display, and the true airspeed, which is taken as you actually consider the wind direction and everything into account, and you calculate the true airspeed. And right down over here, you can see that the heading and the true airspeed of an aircraft, which are pointed towards your right. Which are pointed towards your right, and you have that is the heading of an aircraft. And when a pilot is actually flying his aircraft, he'll be needing wind airspeed also. So let us say that my wind is around 20 kilometers per hour towards northeast, just for an example. So you have your heading, and the wind is blowing northeast like this. So when the wind is blowing northeast, your ground speed or the the tracking speed at the air control system or related to the earth will be a vector which is considered using heading, true airspeed, and the wind speed direction. So you have the ground speed which is in other direction. So the angle between heading or the actual position of an aircraft and the ground speed is known as the drift angle, which is due to air velocity, taking the wind speed into consideration. So here, let us say, and you can also say you have a waypoint of which is being repeated twice or thrice. In the next following slides, you can see it exactly. So, for example, if my aircraft is at one position, I need to go to another position with a certain latitude or longitude, or which is another waypoint. This is actually waypoint are nothing but they are the flight legs which calculate or which help us calculate the position or the actual velocity and actual parameters for the navigation of an aircraft. So keeping this apart, if I continue further, The navigation systems are one of the most important systems. And we have three different types of navigation systems that are in use today. So first thing is ground-based navigation system. Second is air data and inertial navigation system. Third is global navigation satellite system. Okay, so if I say ground-based navigation system, the name itself says ground-based. That means the sensors or the equipments that help me measure or navigate my aircraft are fixed on ground. For example, if you're over a continent like continental Europe or North America, or even let's take India, you're in the airspace of Indian airspace. When you're in the Indian airspace, you have certain beacons that are placed at a certain distance to help the aircraft guide. This is actually one of the older systems that was existing, or we still use it today. These are actually, you have very high frequency sensors or direction measurement DME beacons alongside the NDB beacons, which help us to guide the aircraft. In the second one, you have the air data and inertial navigation system. Air data and inertial navigation system, the name itself says air data. That means everything is present in air. That means the aircraft actually navigates itself, or the pilots can stay in contact with the traffic control, or they can navigate themselves using based on the local data that they are getting from their airspeed and inertial sensors. So air data relies on inertial sensors and other airspeed related data which are taken on board the aircraft. So that has nothing to do with the ground-based beacons that we have just seen. And the third one is global navigation satellite system. The keyword here is satellite systems. So what you can say is global navigation. That means it relies on a set of GPS satellites, which are generally, for GPS to function, you have 8 satellites, which are global positioning satellites that revolve around the Earth all the time. And the second is you have a 12-channel global navigation satellite system, 12-channel receiver, GNSS receivers, which help the aircraft navigate accurately. And the third one is GLONASS. This is nothing but GNSS developed by the Soviet Union. Generally, GNSS or most US-based aircraft or European-based aircraft, they suffice their requirements using the first two, GPS satellites and GNSS satellites. So right now, let us see what are the key differences between all these three kind of data. On the top left corner of the slide, you'll be seeing the ground-based navigation system, the GNSS system. So let us say you have waypoint 1, waypoint 2, and 3. You have 3 different points with 3 different latitudes or longitudes, or three different locations where you have the beacons. Okay, so a beacon is actually referred to a latitude and a longitude. So I have my aircraft which is at a certain position. Its true heading, it has to be taken towards the beacon 2 or waypoint 2 over here, and again further to waypoint 3, and further to waypoint 2 and waypoint 3. So to guide the aircraft, they actually use the beacons that are present at these positions. Okay, apart from these, you have DME4 and DME5 and NDB2, which are actually not in the flight path of an aircraft. They are a bit aside or beside the flight path, which actually gives me or provides me to calculate the error where I have my heading. So for example, if I'm going from my current position, if I want to go from my current position, let's say this is my current position, and I want to go to waypoint 1, and let's say that my true heading is somewhere over here, which is at a certain distance from waypoint 1, let us say D, and I have a certain distance with NDB2, D, and 2. So this distance D and 2 actually gives me or helps me to calculate the adjustment or the drift angle that I need to give so that the aircraft can head towards my waypoint 1. Similarly, if I am traveling, let us assume that in my second iteration, in the second calculation, let us assume that my current position is at waypoint 1, and I need to go to waypoint 2. If at all I am deviating from my paths, I can rely on DME4 and DME5 to give some corrections to get back to my course. So this is how the ground-based navigation systems work. And as I said before, air data or inertia-based navigation systems do not rely on any kind of ground-based sensors. So they are actually, as you can see, the main difference between both of the figures is you don't have these VOR or DME beacons that are present. Even though I am on, let's say that I am over the Atlantic Ocean, or I'm in an ocean where there I have no land to put my beacon. In that case, I can rely myself purely on inertia-based navigation system. There are a couple of sensors that are present in my aircraft, which give me feedback data from the sensor saying that my current, for example, a gyroscope. My gyroscope says my current orientation or my rotation or rollover angle or pitch up angle or this one. All these deviations, they are actually fed up on my navigation system display. So when I have this, I can give some certain corrections. My flight path is actually already planned. So to rely or to guide me back towards my first flight course, I can rely on these inertia-based navigation system, the data that I'm getting from gyroscope or other sensors, to give certain corrections. For example, I'll be going like this. Instead of going like this, if I say that I'm having here, at this point, I can actually rely on the data that I'm getting from inertia or air data to say that, okay, my heading is different. I am not on the exact planned flight path. So I can give some corrections to come back. Similarly, if I'm going like this, instead of going this way, I can give my corrections based on my inertial data. So this is how inertia-based navigation systems work. So you have ground-based navigation systems and inertia-based navigation systems, which are purely different. When I'm talking about global satellite-based navigation system, the schematic actually changes. Instead of relying, I don't rely neither on sensors present on ground, nor on my inertia sensors INS system on board my aircraft. I actually depend on some external satellites which are revolving around the Earth. These satellites, actually, I send up a signal to my satellite and receive signals to my satellites. So when I have this delay, if I have a deviation in my course, this time delay actually will change. So when this time delay changes, there are softwares. I mean, there are the navigation system or the avionics system on board my aircraft will calculate this time delay and compare it with the already calculated time delay with respect to my flight path. Once they do this, they say that okay, there is some error, so you need to give this correction. So I can actually give the correction to bring the aircraft back on course. WP1. And again, I'll send signals, I'll receive signals. It is better to draw solid lines. I'm at here, this is my position. So I'll send signal to the satellite and I'll get signal from the satellite. So this time delay delta T is actually, I'll rely purely on this delta T to get my aircraft back on course. I'm at waypoint 3. So I can get time delays from two different satellites to be more precise. So this is how the navigation system actually works on an aircraft. So what have we seen? We have seen three different types of navigation systems. Okay, navigation systems, I'm not touching it into details because we will actually be seeing navigation system in details in the further course of this in further parts of this course. So I'm just giving you a brief idea about how navigation systems actually work and what are the essential points that we have on navigation systems. So let me repeat. Please do bear with me that I'm going to and fro in my slides. So first thing first, I have ground-based navigation systems. I have air data and inertial navigation systems, and also global navigation satellite systems. So ground-based navigation systems are the one which rely on beacons that are present on Earth, present on land, not on Earth, on land. And the second kind of navigation system is the air data and inertial navigation system, where I purely rely on the onboard sensors, that I have from on my aircraft. And the third one is global navigation satellite systems, which I rely on the satellites that are present on that are revolving around the Earth. So a small example of GPS systems, instead of imagining with aircraft, let us say nowadays each and every car has, or your phone, okay, your phone has a GPS module in it. Okay, your local location is being actually, if you turn on your location, let's say that you are on Google Maps and you are looking for directions from Institute of Aeronautical Engineering to IIT Hyderabad, for example. Let's say it will propose you 2 to 3 different routes. But how is it proposing? You're giving some you're giving some latitude and longitude coordinates, or you're giving some address. In the case of aircraft, it is latitude and longitude. You're giving some address. That is your destination. So when you turn on give directions, it proposes you three different directions, giving based on the traffic conditions and other things you have as per your requirements. You actually change the course of your path that you take. So what happens is the GPS satellite. What is happening? You are relying on GPS data. You don't have any other sensors saying that I have to go from here, take left, take right, and then take the ORR to go to Hyderabad. I mean IIT Hyderabad. Yes, that is there, but that is the big direction that is being given to you or proposed by Google Maps to you, but which relies on GPS satellites. A pure example that we use every day, a small example that we use on a day-to-day life is nothing but GPS on our phone. We can see various other uses of GPS. And you can say how come aircraft can navigate itself using inertial sensors. For example, let us say you're playing, I think every one of us know the game Temple Run or Subway Surfers, most probably Temple Run. So the sensor that is the gyroscopic sensor that is present on the motherboard of your phone, when you tilt the phone, the runner or the thief will actually change. Will actually move his course. So that is how the same thing in an aircraft. When I have a gyroscope, if I'm doing a roll motion movement, it actually calculates the angle that I have drifted apart from my first course. Okay, and to bring back, it recalculates the angle or the corrections that I need to give to the aircraft control surfaces, or the pilot needs to give it as an input. It calculates and it suggests me. So if at all, if you are relying on autopilot systems purely work on inertia and also GPS satellite. Nowadays we only see global navigation systems and inertial navigation systems in our aircraft. And inertial navigation systems are also being used in quadrupter drones. For example, let's say that you're doing a small workshop on quadrupter. You have the motherboard, the electronic controller unit, ECU, speed controller, ESC, or whatever name you give. You have a chipset where you have other sensors that are placed. So based on the corrections that you need to give, it actually decides how much thrust and where should I give the thrust, and how should I go, or how should I change the course of my flight path. So these are the navigation systems that we will be dealing in our next chapters of this course. So when time comes, I'll be explaining each and everything in detail. Okay. So for the moment, we only leaving at this, and the next topics that I'll be dealing in the next class are actually displays that are present in the cockpit and the communication systems that that are required for the navigation of an aircraft between its path and also the other aircrafts or the air traffic control systems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.